turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
Questions. Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists. Hello, welcome to this week's Naked Scientists, the programme where we strive to bring you the latest breakthroughs in science, technology and medicine. I'm Chris Smith. Coming up, could lab-grown mini-guts help us to crack Crohn's disease? Also, is the universe organised a bit like a bagel? Well, I talked to one cosmologist who's trying to figure it out. And we hear from the engineers who've recreated a 115-year-old cricketing contraption that actually bowled out an Australian legend back in the day.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
Up first this week, mini-guts, grown from cells collected from the linings of the intestines of patients with the inflammatory bowel condition Crohn's disease, are helping scientists to better understand why some people develop this chronic and disabling syndrome. Matthias Zilbauer, who's Professor of Paediatric Gastroenterology at the University of Cambridge, has found changes in the level of activity of genes linked to how the gut lining cells interact with the immune system. This is down to a system called epigenetics, and it involves chemical groups being added to the DNA to alter the extent to which different genes are turned on or turned off. He doesn't yet know why he's seeing the changes he is, but it seems very likely that the environment we're exposed to in early life probably plays a major role. And by revving up these immune-related genes, the intestinal lining cells are much more likely to provoke the inflammatory damage that characterises Crohn's disease. And of course, if we understand how the disease gets started, we're one step closer to stopping it.
The fundamental question is whether the cells that form the inner lining of our intestine have a sort of a malfunction in patients that suffer from a specific condition called Crohn's disease, which is a form of inflammatory bowel disease. And generally speaking, it's our immune system attacking parts of our body, and in this case the gut, causing inflammation. So the unknown here is what particular role the cells of the inner lining of the gut play in this whole disease. And we used a fairly novel approach which allows us to grow these cells in a dish after we've taken them from a real piece of gut from these patients.
Effectively, then, you're growing sort of mini intestine in the dish. What does that look like, and how does that take us forward?
Correct. So we are only growing that particular cell type that forms the inner lining. And they look a little bit like cauliflowers, either sort of balls or cauliflowers with tiny little finger-shaped structures. And it turns out that these structures look very similar and perform similar functions than the cells do in the real gut.
How does that help, though?
Because for the first time, really, we're able to test the function of these cells taken from patients with the real disease, and also compare that to cells that were taken from patients that do not have the disease. And this allows us to figure out, is there something wrong? And if so, what is it that goes wrong?
And do you see differences?
Yes. We've seen quite remarkable and striking differences. And that has led us to identify a specific mechanism, which is called epigenetics. And that mechanism regulates one specific function of the cell. And that function, which is called MHC class 1, that is able to attract immune cells. And so this now could explain why in these patients, when you have a cell type that recruits these cells to the gut, why that's inflamed.
In summary then, these cells that you're studying, they have some kind of change to the way that genes are being turned on and turned off in those cells, and that is affecting how they interact with the immune system. But how did they get that change to their epigenetics in the first place?
That's exactly a key question that is still outstanding. So we believe that these epigenetic changes that led to that malfunction were there when the disease started. If we are right and that's the case, then we speculate that these changes have probably occurred earlier in life, perhaps long before the disease has manifested itself. And there is lots of studies that show that our environment has changed over the last 10, 20, 30 years. And these changes seem to correlate strongly with a dramatic rise of these conditions, of inflammatory bowel diseases and Crohn's disease. And so the idea is we are being exposed to different environmental factors that impacts on our cell types, on the way they function. And if that goes wrong, we end up with disease.
Do you think that could be shifts in the microbiome, the composition of bacteria that live in the intestine? It could be the kinds of foods we're exposed to at what ages and that kind of thing. What do you think is the influence that causes that switch to have this particular behaviour in these cells?
So I believe it's likely to be a combination of all of these factors, of many factors. It's going to be things like the type of foods we eat, processed foods, maybe more or less meat, which all impact on the microbiome, but also things like in exposure to microbes. Our environment is becoming increasingly sterile. Everything is clean. We are not being exposed to this kind of microbial world that we may have been exposed to 50 or 100 years ago. And so our immune system is no longer trained or challenged to defend ourselves from these microbes, which it was originally designed to do so.
Obviously, one way to test this out would be to either reverse the changes that you have seen in your cells and see if they start to behave more like healthy cells, or take healthy cells and impose those changes that you've seen in the unhealthy cells epigenetically and see if you can make them behave in an unhealthy looking way. Have you gone down that path yet?
That's exactly the way we're going down at the moment. We're trying essentially to find out what's caused these changes, because that would allow us to prevent the disease from developing in the future, potentially. We believe that in order for these changes to happen, your cell type has to be in a sort of a developmental state that allows these changes to occur. And so we've got access to human fetal organoids, gut organoids, and we're exposing them to all of these factors, to microbes, to inflammatory stimuli, to certain food types, but also the interaction with other cell types, immune cells, and then see what happens. How does the epigenome change, and how does that potentially alter the cell function?
Matthias Zilbau there at the University of Cambridge, and that study, appropriately enough, has just come out in the journal Gut. Into space now, and to the topic of topology. This is actually a term that's used to describe attempts to determine the overall structure of things like the universe, and it stumped scientists for years. Is the universe a flat sheet, which researchers dub boring, or are bits of it connected back into themselves, a bit like a doughnut? A new international partnership called Compact is attempting to get to the bottom of it, and Andrew Jaffe, who's at Imperial College, is part of the team. I've been speaking with him to hear more about the problem that they're grappling with, beginning with getting my own head around the difference between shape and topology.
Shape can mean lots of different things in lots of different contexts, and even in cosmology and astrophysics, it can have more than one meaning. So we have to be very precise, and that's why we use this word topology. So let's step back and think about the different shapes that things can have. Well, they can be round and curved, they could be flat and have sharp edges, and the part that's about curvature we think of with a different word, geometry. So the geometry talks about how curved a surface is, for example. So a ball has a particular kind of surface, a saddle has a surface, a sheet of paper has a curvature. All of these things have curvature and therefore geometry. What we're asking here is not about the curvature of the universe, which is a different question, but the topology of the universe. And the topology is about, well, it's sort of about holes and handles and the way different places in the universe are connected to each other. So the best way to think about this is to think about a video game. So remember the kind of video game where the character goes out the right-hand side of the screen and comes right back in the left-hand side of the screen, or goes out the top and comes right in the bottom. Well, the screen is flat. It has a flat geometry, but it's connected by the left and the right and the top and the bottom, and that's the topology. And what's weird about that is that it's the topology of the surface of a donut or a bagel. Now think about that. So take the two edges of the screen, the right and the left edge, and curl them around so that they meet. And now you have a tube. Then take the top and the bottom and curl those around, those circles that you've made by curling the left and right together. Take those and make a bagel. And that's the kind of thing that we're searching for, but not on a two-dimensional screen, but in 3 dimensions, where now not only do you have left and right and top and bottom, but you have front and back. But you can do the same geometrical and topological manipulations and make something which is like an extra dimensional donut or bagel. And we call that surface in general a torus.
And why do we think that the universe might have one of these exciting topologies? It's not just a flat, smooth thing blowing up like a balloon.
The simplest answer is why not? There's nothing in the physics that we know to tell us what the topology of the universe should be. So Einstein's theory of general relativity, which is about gravity and also dictates the expansion of the universe that you just mentioned, says nothing, literally nothing, about the topology of the universe. So we need to check because there's no reason not to have it. And if you look at the way quantum mechanics and general relativity, that is to say the science of the very small and the science of gravity and the very large interact, then we have at least some reasons to believe that in the very, 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 very early universe, 10 to the minus 43 seconds or so old, that's when topology might have been very fungible, very changeable. It could just change because of quantum mechanics, and that the most likely thing would be a small universe that is small in exactly the same way that this torus is small, that the left and right and top and bottom and front and back are continuous with each other, and you get these torus-like shapes.
And how is Compact trying to get underneath this?
Well, we cosmologists more generally have been looking for the kinds of effects that an interesting topology might give us in our data for at least 75 years. And the first way we looked at it was, if you go back to this video game, if you're living in the video game and you look to your left, you'll see the back of your head. Where you look up, you see your feet. There's no reason why your line of sight doesn't just keep going. And so that's the same thing we look at here. So originally, people just looked for duplicates of the local universe far away. So they say, do we see the Milky Way millions or billions of light years away? And of course, that's a hard observation to do, but nonetheless, people have said, no, we don't think we see that happening. So then, somewhat more recently, since about 1990, we have actually gotten hold of the most distant pictures of the universe we can possibly get by looking at something called the cosmic microwave background radiation, which is light from about 400,000 years after the Big Bang, so almost 14 billion years ago. And what we want to do then is look for repeated patterns on that surface of the sky. And we also don't see them there. But it turns out that this torus that I mentioned, this donut shape, the surface of this donut, is not the only topology you can make. There are, roughly speaking, 18 different topologies that even if you're just living in a flat, geometrically flat, right, no curvature universe, you can have. And then if you allow the universe to have curvature, there are literally infinitely many more possibilities. So part of our job is that kind of fun maths job. But what we really want to do is go beyond that. We want to say, are there observations we can make that might give us further hints on the topology? And the answer to that is we think yes. So our nearby universe, if you can look at things on a fine enough granularity, and you can do a census of essentially everything inside the CMB, then that gives you hints about the way things are distributed, even outside what you can see. That's sort of the place that we're just getting to now, to come to grips with how we might do those observations using some future observatories and their successors, because even the near future observatories probably won't be enough, but their successors, which will enable us to do a census of everything or almost everything that's in the visible universe.
Fascinating endeavour. Andrew Jaffe there, he's the director of the Imperial Centre for Inference and Cosmology.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
You're listening to The Naked Scientists with me, Chris Smith. Still to come, the Cambridge engineers who've recreated a 115-year-old cricketing machine that gave the Aussies a run for their money back in the day. Before that, though, New analysis suggests that previous infections with SARS-CoV-2, the cause of COVID-19, can reduce the risk of getting symptomatic illness from other members of the coronavirus family, including the ones that cause the common cold. And it also seems to work in reverse. Recent cold infections can confer protection against severe COVID-19 disease. The reason Manish Sagar from Boston Medical Center at Boston University has found is that genuine viral infections stimulate the production of immune white blood cells that recognise and attack a part of the virus that is common across the whole family of coronaviruses. This doesn't happen with the vaccines we're making, which stimulate only the production of antibody molecules and don't include the component that the cells are recognising. Knowing this means we might be better placed in future to engineer vaccines that can induce this sort of cellular response that can combat a range of coronavirus threats, including, potentially, even those that don't exist yet.
We looked at people who had documented SARS-CoV-2 infection. We looked at people who had documented COVID-19 vaccination. And we looked at people who did not have SARS-CoV-2 infection or COVID-19 vaccination. We followed them and saw whether they subsequently got infected with another coronavirus related, but not identical to SARS-CoV-2. And what we found was that people who had prior SARS-CoV-2 infection were around 50% less likely to get a related coronavirus infection, which we call the common cold viruses, as compared to those who had only a COVID-19 vaccination or neither exposure. And then we went on further to look at the immune response differences among these three groups. And what we found was the cellular immune response was probably what was dictating the difference that we observed.
We saw hints of this during the pandemic, where there were people who emerged who just did not get infected clinically. They weren't becoming unwell with SARS-CoV-2, and scientists speculated perhaps they had been exposed to other members of the coronavirus family in anticipation of being exposed to SARS-CoV-2, and that's perhaps what protected them. Why do you think, though, that this is more of an unbalanced seesaw? You saw a much more profound effect with SARS-CoV-2 infection protecting against other coronaviruses than perhaps the other way around.
You're right. There are definitely people who are not getting infected with SARS-CoV-2 or not having severe disease, and we don't know specifically the reason for that. At the start of the pandemic, we looked at people who had documented common cold coronavirus infections previously and those who did not, and we followed them subsequently, and we saw what happened when they got infected with SARS-CoV-2. What we found was that those people who had a documented previous common cold coronavirus infection were at the same risk for getting infected with SARS-CoV-2, but were much less likely to get sick after getting infected by SARS-CoV-2. And this was the basis for thinking that there is an immune response that's cross-reactive among these family members of viruses that are related but not identical. And this is important because if there is future coronavirus that comes out, our ability to potentially develop a vaccine that's as effective as the COVID-19 vaccination, but maybe even better, is if we start thinking about how do we generate this cross-reactive immune responses among the coronavirus families.
The common coronaviruses cause about 5% of the seasonal colds that we get, which means most people over the course of their lifetime have run into them all, because there are a handful of them, multiple times. So why then isn't everyone protected against SARS-CoV-2 in the way that you're saying, if it's that good at making these cell-based immune responses that are capable of preventing or mitigating severe disease?
Yeah, that is a great question. And I don't have an absolute answer for you, but I suspect the severity of the common cold coronavirus infection that you get may dictate how good of an immune response that you get. So that's one possibility. The other possibility we should always note is you're absolutely right that people get infected with coronaviruses at a frequency of approximately 3 to 4 years. So those people who have recently had documented coronavirus infections within the past 3-4 years, as opposed to those who had it greater than 3 to 4 years, those people may have an immune response that's much more robust It hasn't decayed over time yet, and that's why there's an ability that's different among these people.
So in this study then, were you able to go after what it was about the immune system that gave the protection that you saw? People who've had a bad dose of SARS-CoV-2 demonstrably measured they were clinically ill, they're now protected against common cold type coronaviruses for a while. Have you found the cells that are doing that, and can you prove what bit of the virus they are reacting to, and therefore you know it's a valid claim that that prior infection is causing them to be protected in the way that you think they are?
This is an associative study, so we cannot definitely state that this is mechanistic, but what we can say is it's not antibodies that are making the difference. The reason this finding is important is because most vaccine efforts are aimed at generating broad antibodies that will target all coronaviruses, but potentially they may not provide the broad protection needed. So in our study, what we found was that the other arm of the immune response, the cellular immune response, which kills virus-infected cells, was important. And importantly, the cellular immune response targeting a very conserved part, that means a part that's very identical among the different coronavirus families, was the one that was potentially important for providing the protection that we observed. And this part of the virus is not currently incorporated in really the COVID vaccines that are the most common around the world. They only target really the spike part of the virus and not the part of the virus that we identified that may be important.
Manish Sagar from the Boston Medical Centre at Boston University. Well, back to Cambridge now, and engineers at the University of Cambridge have recreated a wooden machine that bowled out an Australian international cricketer in 1909. It was originally designed by the famous mathematician John Venn, who gave his name to the well-known Venn diagram. Cambridge University's Hugh Hunt set a challenge to his colleague Thomas Glenday to recreate the contraption. I went along to meet the pair of them and see it in action.
We're here in the workshops of the Cambridge University Engineering Department, and just down the road is Caius College, Cambridge, and a fellow, the senior fellow of Caius College, Cambridge, was a chap called John Venn.
Ah, now that's a name that rings a mathematical bell. Venn diagrams?
Venn diagrams, exactly. Now, there's a lovely stained glass window in Caius College of a Venn diagram. It turned out that one of his interests was cricket, and back in 1909, he built and patented a cricket ball bowling machine.
And how did this come to light?
Last year was the 100th anniversary of Venn's death. In the interests of finding out things about Venn, to celebrate Venn diagrams and mathematics and stuff, as you do, you search on the internet, and up came this photograph of this chap Venn standing in front of a gizmo, as it turns out, in Cambridge at Fenner's cricket ground on the day of an Australia versus England 3-day test match.
Did it get to bowl at the Aussies then?
Yes, so the story goes, it was in the newspapers, Victor Trumper, who was an Australian top batsman, failed to hit the ball 4 times in a row, I think it was. And this was a real coup. Now, it wasn't a particularly fast machine, but boy, it put a lot of spin on it.
But how did you end up building one? We are standing next to what I presume is a replica.
Well, this is a replica of John Venn's machine. The photograph from Fenner's cricket ground tells us a lot about what it looked like, and the patents, the diagrams in the patents. But still, it was a tough job to figure out how to build it because there were no kind of working drawings. So I went into the workshops at the engineering department and I said, "Hey, Thomas, do you want to do this?" And he didn't say no.
And you found this guy who it fell to you to try and recreate something from 100 years ago. How did you go about it, Thomas?
So the machine consists primarily of a fairly heavy base, and then it has a front and rear frame structure that supports effectively 2 guide rails. And then you come to really the business end of it, which is the throwing arm. So there's a pivot mounted on that bottom platform and a approximately 7-foot arm, which is a single piece of timber. And then that piece of timber is suspended between the 2 frames with the main power elastic, and then there's a rear elastic that catches the arm and prevents it from sort of going full scale and smashing the end of the machine.
I'm intrigued, though, why there is a sort of cup that holds the ball, but on the other side of that cup is a thing that looks a bit like you would throw around with a Diabolo stick. What is that?
The top of the arm houses the contraption that both holds and releases the ball, but it also has a shaft and two bearings inside that imparts a spin on the ball, and that's really the critical part of this machine. So the rear section you describe as looking similar to a Diablo effectively acts as a cotton reel, and when the machine is cocked, a cord is wrapped around that reel, and as the machine goes through its motion, that cord is effectively ripped, which puts a spin onto the bobbin, onto the ball, and the ball's released with significant spin on it.
When Hugh said it produces hideous amounts of spin, the ball is going to leave that really, really, really spinning. Is that not a bit unfair on poor old Trumper when he tried to hit that?
I would say it was unfair on Trumper, but there you go. But I reckon this machine could really reproduce a prodigious Shane Warne leg break. A lot of spin, not hugely fast, and maybe that Gatting ball we could reproduce with this machine.
Put simply, you load a ball up there into the cup and just pull this thing back, a bit like a medieval trebuchet against the elastics, let it go, and it just launches the ball in the direction that the arm swings back against the elastic and puts that spin on it. But is it actually any good?
It's a very consistent machine. The ball is going to pitch in the same place, and then you're up to the foibles of the pitch and exactly how the ball lands, which is what real cricket is about.
But what's the critical thing about making balls spin? Does that really make a difference to how they move?
A ball spinning through the air curves around, but when the ball lands on the ground, if it's spinning, it will also grip the ground and move off in a direction depending on which way it's spinning. So both of those things are really important.
Oh, so it's a two-dimensional trick, really, because it's going to move in the air, and probably also as the speed of the ball changes, it's going to move different amounts, but it's when it hits the ground, it's also going to throw the batsman off.
Absolutely. So when the ball hits the ground, it can move left or right, but if you've got a bit of topspin on it, it can accelerate onto the bat, or a bit of backspin on it, and it can lift up. So spin is a pretty critical parameter.
Have you had a go, Thomas?
Have I faced the machine? I haven't.
You didn't dare face your own invention.
I've been responsible for operating the machine in a safe fashion. So no, I haven't actually faced it myself. But
where have you tested it?
We've taken it to 2 events so far. So the first event was across the road here in Cambridge, and that was so that some of our top Cambridge University players could face it. On Monday this week, we took it to the Essex County Cricket Ground, where they were putting on an event to sort of bring maths to life for young children, and in fact the older side of the population, where some residents of a care home came along. So it was really nice to see that multi-generational interest in something that does bring maths and physics into everyday life, that in this case is the game of cricket.
Should we fire it?
Let's fire it.
Do you have to be really strong to cock this thing, or is it not too bad? Oh, yeah, you do have to be strong, don't you? It's taking two massive great blokes to pull this thing back.
So what we've got is a nice handle here, which we can use to release the mechanism.
I'm going to let Thomas do it so I can watch and see. For people at home, basically, I likened it to a trebuchet earlier, and that's basically what we've created now, because it's cocked right back against the elastics and locked into position. Thomas is standing here with the cord in his hand.
3, 2, 1.
We just took out half the engineering department's extraction equipment, I think, with that.
It was pretty good.
It's certainly got some power, Hugh.
It has got some power. And I think that people who face this for the first time, certainly back in 1909, would have been completely astonished by this. Because you're used to the idea of watching some lumbering bowler come in and you can see when they're coming. Oh, yeah, here they come, here they are, okay, ready, set, go. But this is, it's a little bit like firing a gun or something. You don't know when it's coming. I think that would have been quite hard to deal with.
How's that? See, we can occasionally beat the Aussies. It's at least something related to cricket. That was Hugh Hunt and Thomas Glenday there at the University of Cambridge. Well, into bat next is my colleague James Titko, who's going to take on this mathematical quandary for listener Andrew.
Hi, I've been doing some GCSE practice maths papers with my son today. I find it quite amazing that I can still answer some of these questions, given that I've not used any of this maths for probably 40 years. And we both agreed that remembering maths feels quite different to recalling facts for other subjects. Why is that? And is a different bit of the brain used to remember maths? Thanks.
Thanks, Andrew. And this one's sparked a really interesting conversation on our forum. Evan's written in to say, I always found maths easier than history because maths has a regular logical structure, while I saw history as a bunch of random dates with no structure. My wife was the opposite. Maths was random facts that seemed to have no structure, but she enjoyed history and art. Thanks, Evan. When it comes to exam success, we're relying mainly on our semantic memory, as it's what allows us to recall facts and concepts. But what's the difference between remembering a historical date versus how to do trigonometry? Well, I've asked Catherine Loveday, a neuropsychologist at the University of Westminster, to help us with the answer. Hello, Catherine.
Hi there.
What is it about maths that might make it easier to remember?
Well, maths is very much a doing subject, so we tend to do tasks and there's a lot of repetition in those tasks and there will be a deeper level of processing quite often. So, for example, if you use a formula, I can still remember lots of mine as well. If you use that same formula lots of times, it becomes almost an automatic piece of knowledge for you. And also, you're often coming at different problems from different angles and having to use that same formula in different contexts. And that allows you to process more deeply. And we know that both of those things, repetition and the depth of processing, both of those will make memories stronger.
People who are good at maths, there's this sort of rhythm they get into when you watch them. And it feels like the hardest part of that is starting it, isn't it? But they can really get into a flow, can't they?
Yeah, that's a really good point. And we know that creative flow is a measurable concept that happens. And I think there's another aspect to it, which is the sense of reward. So we know that memories become strengthened when there is a reward at the end of it and you feel good about something. And I think there's something about maths that if you can do it, there's a real sense that you have achieved something, that you've got it right at the end of it. It's not like history or English where you write an essay and, it's kind of right, or it may be good or it may not be good. With maths, you get that very quick, distinct answer. And that is a real reward. And the brain will learn things better when it has that.
Although what you've said may be true for people like Andrew and those on our forum, who I have to say it seemed largely agree, others might find that they slip back into other subjects more easily.
Yeah, I think that's true. I think for some people, maybe a piece of poetry might really stick. Again, there's lots of repetition there. And sometimes even things like history dates, because people often do very active revision around those. So they repeat them lots of times. And again, it comes back to this reward pathway. If we are interested and motivated and driven by these particular subjects, then we are more likely to remember those things better.
Fascinating listening to you. Thank you so much. That's Catherine Loveday. She's a neuroscientist at the University of Westminster. Thanks to Andrew as well, of course, for sparking that conversation. Next week, we're answering this question from listener Janie. They ask, how do wind turbines work when the surface area that catches the wind is tiny compared to old-fashioned windmills?
And if you think you know the answer or you have a question of your own you'd like to pitch to us, then why not drop us a line? It's chris@thenakedscientist.com. You can also join in the discussion on our forum. That's at nakedscientist.com/forum. Before we go, do please consider, if you enjoy this programme and what we do for you each week, giving us a donation to support the show and keep the programme on the road. It's nakedscientist.com/donate. This is a huge help to us. Thank you to everyone who does support us each month. But if you would like to show us your appreciation, we've made it very safe and secure. You go to nakedscientist.com/donate and there is a secure web interface there where you can either make a one-off contribution or be a regular supporter of what we do. Please do help us out. nakedscientist.com/donate. That is it for this week, but do be sure to tune in on Tuesday because Will Tingle is going to get to the root of how our changing climate is affecting our trees. The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm Chris Smith. Thank you for listening, and until next time, goodbye.